Okay, so next up we have David McGaw, who is also going to talk about Doppler shift type of observations, but using a slightly different band. So David McGaw, N1HAC, is a research engineer at Dartmouth College, and he's going to talk about traveling ionospheric disturbances observed using Doppler measurements of clear channel AM broadcast transceivers. So I'm going to stop Steve sharing. So go ahead, David, you can take control.
I'm David McGaw, N1HAC, research engineer at Dartmouth College, also vice president of our local club, the Twin State Radio Club. And we've done a, is there a way to hide the panels? It's covering my presentation here.
You can slide them off to the side, but we don't see them on your screen share, so they're not interfering with what we see.
Okay, good. How am I going to? There we go. We started out with this research with an original proof of concept done in 2012, and a paper that was written by Mike Chilcott and others, published in AGU Radio Science, and a number of undergraduates were also involved. This was done using the MIT HamSCI ISIS receivers that are distributed around the Northeast. And we had help from Juha Virtanen. This is the antenna that we used, had them at a number of sites. It's a smaller version of what we use for our HF research in the polar regions. It's about 7 feet on a side, loop antenna into a low noise preamp. And we had systems at Dartmouth, at HamSCI, and over at Siena College in upstate New York. Picking up, in this case, WGY from Siena, from Schenectady, and WBZ from Boston. And this is the data that we got from there. As you see that it's shifting a few hertz, a few tenths of a hertz, plus or minus, due to Doppler shifts from the ionosphere. You'll also notice that the carrier frequencies can be slightly offset. This is a normal thing for AM radio stations. And this is an analysis that was done in the paper, lining up our Doppler shifts with the HamSCI Digisond, GPS total electron content measurements, and Wallop's SuperDarn, showing that the effects that we're seeing correlate with other ways of studying this. We changed for further study to a newer antenna, much smaller, essentially same preamp, but the large loop is much higher sensitivity than we need. So this works out well. It's two turns instead of the single turn, works out to the same effective inductance, but is better suited for what we're doing, and have deployed those to give them a try. The next, this next stage in our development was to deploy them in the same locations. No, actually, we added Jenny Jump in New Jersey, and then picked up several radio stations, Boston, Schenectady, and New York City. This time we were using the USRP software-defined radios, and we've gotten new results from that, as shown here. Shifting, a few tenths of hertz, and showing that we do indeed get good Doppler shifts off of these signals. So then we started development of our own system. I was showing it at the HamSCI conference a couple years ago. This is at HamVention 2019. We have now deployed the system out in a number of places. This is the receiver. It uses a 12-volt power supply. If we needed to put it on like solar panel or whatever, we could. It has an input for the preamp. We use a solid-state hard drive. This is showing it with a MiFi cellular radio interface. As one of our sites, we do not have access to wired internet. That's the front panel. It uses a Raspberry Pi, so you see that over on the left. We have a GPS internally, and we bring that out so that we can monitor it. GPS antenna going in. We have a attenuator on there because we're varying different distances from local radio stations, so we can pop in an attenuation as needed to prevent overload. This is the inside of the receiver, and made up of a number of components, and this is what's in there. We'll start on the lower right. We have the power input and a bias T for the preamplifier out to the antenna, remotely powered. Then it runs into the attenuator. Then it's fed to the Noelec Hammond up converter, because we're doing the AM broadcast band, and the SDR that we're using in this doesn't cover that directly. Goes into the RTL SDR. That's 24 megahertz and up, so that's why we run the up converter. There's the GPS disciplined oscillator that is our frequency reference. Because we're measuring things on the order of tenths of hertz on a megahertz, that's 10 to the minus 7th. We clearly need a reference frequency much tighter than that. That goes into the frequency synthesizer, which is a TI chip that develops 28.8 megahertz to the RTL SDR, which is its primary clock frequency. And then we create a 129.6 megahertz local oscillator for the up converter. The up converter, as it comes, is 125 megahertz internally, but 129.6 is harmonically related to 28.8, and it does fall within the pass band of the up converter local oscillator chain. We have a 12 to 5 volt DC-DC converter internally, and a couple of regulators that are used to develop voltages that the frequency synthesizer uses. And finally, we have the Raspberry Pi, which is the processing heart to the system. And the Raspberry Pi does yeoman service for us. What we're doing, we're running the RTL SDR at a 1 megahertz sample rate, and pulling in 600 kilohertz to 1.6 megahertz. And then the Raspberry Pi decimates that a couple of times. First, breaking it into individual AM station channels, and then it filters it further so that we're only looking at those 1.5 hertz channels, so that we can actually discriminate the Doppler shifts. So we have receiver sites. These are the designations of our receivers. AMD1 was a prototype that went to South Africa and was used there, but number 2 is the one that we keep at Dartmouth College. AMD3 is at Schenectady, New York, courtesy of MIT Haystack, Phil Erickson for citing that. AMD4 is at Jenny Jump, New Jersey, courtesy of NJIT and a number of individuals that have helped with that. AMD5 is at UMass Dartmouth, which is down on the coast near Cape Cod, and courtesy of Dave. No, that's I forget who we have that there, but they're with the Maritime department there. AMD6 is at Cornell, courtesy of David Heisel there. And then AMD7 is pending, will be sited up in Messina, New York, to develop a ring of receivers around Schenectady and its clear channel station there. So these are the radio channels that are monitored from our system. WGY Schenectady is sort of our primary at the moment that we're looking at. But we have a number of them from Montreal, New York City, Toronto, Boston, and the one I used to listen to the Red Sox on, Hartford, Connecticut. This is our data as we receive it now. We're kind of on the early stages of plotting and analyzing. So this is a couple of panels of our that are coming out that's got a few hours of data. I've plotted this to show starting at during daytime on the left, and you can see the signals coming in as sunset sets in, and then further on into the evening and nighttime. You're seeing Doppler shifts coming in. And then this is a series of 3 panels of those 4, the ones to the right. I wasn't quite sure how to show this, so hopefully I can flip between them quickly. But this is the Dartmouth, Schenectady, and UMass Dartmouth on a night recently when things were moving around. And I think you can see how the Doppler shifts correspond, but are occurring at different times. And that is actually the end of my presentation. Are there any questions?
Questions. Thank you, David.
Yeah, I have a question on behalf of Jay Swartz. So the question is, are there any plans to make the AM Doppler receiver available for purchase as a kit or fully assembled?
We hadn't planned on that. We can certainly document it so it could be built by others.
Okay, and Anton has a question, Dr. Anton Kashcheyev. Go ahead. Anton, go ahead with your question. Anton, are you there?
Nathan, he just muted his mic.
Oh, okay. How about now? He's unmuted. Okay, maybe we'll come back to you. Are there any other questions?
This is Phil. David, you had to modify the up converter, I think, from the way it came when you just ordered it, correct? Was that something that was supported by the manufacturer, or was that something that you had to sort of reverse engineer?
No, and then yes. Well, what it is, the original ones that we got, I had to pull the oscillator out and tie in direct. But it turns out that the newer ones have a micro RF coaxial jack on them. And I was just able to drill a hole and buy a interface cable from DigiKey and pop it in. I just had to change disable the onboard oscillator and put the external local oscillator in. They did think of that on a second further revision.
That's really great.
Now the RTL SDR, I did have to hand patch that one. But again, you pull the oscillator and there are some holes there that it's easy enough to put a coaxial cable into it and run a jack out to the outside.
Another question?
Yeah, Anton got his through the chat here. Let me reiterate it. So his question is whether David has plans to reconstruct TID properties, e.g. velocities, it's moving in here, e.g. velocities, period, wavelength, etc., as he has multiple sites and can do it using interferometry.
Yes, absolutely. That's the intention of this system. And this is under my boss, Dr. Jim LaBelle at Dartmouth, and he will be giving a talk tomorrow. And maybe he will address some of that, as well as the other research that we're doing.
Okay, I have another question, actually, if we have time. Question from K6OIK. How do you distinguish between Doppler and apparent Doppler due to interference from other co-channel signals at night?
Well, that's a very good question. We haven't quite worked that out. In fact, I think we're seeing multiple stations coming in. So that would be an exercise for the student.
David, it occurs to me, like WGY, I know in particular, is a clear channel station, which in theory means they're supposed to keep that lane clear, but I don't know out to what distance they keep it clear.
Yeah. Well, that's an interesting point, that these stations used to be truly clear channel, but I've noticed that a number of them have other stations on the same frequency within distance that we would probably see them at night. So it may be distinguishable by amplitude, but also each one of those stations has a set frequency offset from the center channel. Now, actually, some of them have a very odd oscillation on them that we saw. Maybe I can reshare here for a moment. And in fact, the one that let's see, which one of these is, yeah. If you see the bottom, next to the bottom station, it's got this oscillation on it. It's also very much offset. And it's the only station we've seen that particular oscillation on. But it's not, we have to wonder what is going on there with the station's frequency. They're not as controlled as they once were by the FCC. So, and we haven't found specific documentation of offsets, though there are SWLs, or should I say MWLs, out there that do document such things.
Well, thank you very much, David. And yes, let's all thank David. I guess we need some way of having virtual applause on these things. We haven't quite figured that out.